system, we say there are two things we can detect in the flame, either the light or the heat. And somebody said that the heat is too slow to react to, so we try to detect light. These are the stack mounted control. You can see it's called stack mounted because it's mounted in the stack of the boiler. And there's a bimetal here that expands and try to tell the controller there's heat or there's no heat, but it takes too long, an average of a minute to react back and forth. And again, since it's in the stack, it burns all the time and gives a lot of accumulation in it, which is something unproductive. We talked about the cadmium sulfide. How does it work? It changes resistance with light. And we saw this in action in the lab. We put it in the light and the resistance is very low. What is the resistance in the dark? Above 10,000. Very high. In the light? Less than 1,000.
1,000?
Less than 1,000.
So that's all the cancel.
Huh?
That's all the cancel.
Yeah, change resistance.
So you say 100 times 16. I know it's on the board, but it was more than 10,000.
Okay, you gotta remember that. This question is gonna be in the oil burning exam for sure. So in the dark?
So between 400 and 1,500?
More than 10,000. Also equal to 1 kilo more. It could be 3, it could be 2. As long as it's more, that's fine. And the light less than 1,000 ohm. Also 1 kilo ohms. It's a little bit counterintuitive because you'll think in the light it will increase, but no, in the light it decreases.
So it increases in resistance, so it doesn't turn on the burner because there's no flame.
Exactly. It becomes too high, the current is too small, it cannot go through it to make it zoom. When there is no light, there is no flow of electricity that takes place inside the control, and the safety switch will be locked out. There is no light, there is no flame, resistance is high, the flow of electrons will be stopped by this high resistance. So if we have high resistance, the flow will not go through it. And we said everything is conductive at the right resistance, the right voltage. So if we have high resistance, it's not going to go through it. And it is measured and calibrated, so it will not go through that amount of resistance. 15 to 45 second delay for the valve and for the safety timing. Safety timing was 45 seconds. Then it was reduced to 30 seconds. Now it's 15 seconds. So if you go to the first generation, that will be 45 seconds. So this old control is the first generation, and that's 45 seconds for safety. This one, around 30 seconds. This one, the new one, 15 seconds, which is the code now. So the code is going to be 15 seconds. In the oil burn exam, they're going to ask you about the code, and it should be 15 seconds. So, and this is guaranteed to be one question in the exam. So now you have two questions.
15 seconds.
Yeah, yeah.
So you said the longer one was not there.
Huh?
The 45-second one is like safe, is more safe, right?
No. 45 seconds is too long.
Oh, okay.
So they want to be shorter and shorter. And why did that change? Because now we can. There are more sensitive and more reactive equipment. PV cells produces electricity. It's a different thing. What the PV stands for? Photovoltaic. Photovoltaic cell. It does not just change. It does not change resistance. What does it do?
What's the second one?
Voltaic. If I ever spelled that right, but
Produces
you get the idea.
electricity.
Huh?
Produces electricity.
what does it produce? Current, voltage, resistance? Voltage. Photovoltaic is very similar to what you have in your calculator. It's what you have in your roof. That's photovoltaic cell. Photovoltaic, it does use photons from the light and transfer that into voltage. So we can use photovoltaic cell to produce voltage, but they are not, and that will detect light, but that is not used for this residential applications.
That's what the second word.
Huh?
That's what the second word defines.
Yeah. Yeah. There are also infrared detectors. They detect infrared, which is the waves coming out of the heated system. Again, those are all light sensors, but this is the only one that we use for residential for the time being. There are also thermocouples. What do? They produce voltage. So these two will produce voltage, and based on that voltage, you can activate the circuit or have a sensor that when it's activated, it will open or close a relay. That's not that difficult to control. However, based on the speed and the control configuration, we can pick one of those. You'll see those in the industrial burner, but not in residential. We'll go over them. Take your time, write them down. We will repeat those over and over again, but they are very important.
I read somewhere that it's between 400 and 1600 grams.
I don't think so. For the cadmium?
Yeah.
For this application, it has to be between 1,000 and 10,000.
For this
Yeah,
application.
but you can change it. The one in your wall probably is different, in your bathroom, same idea, but it has different limits. Why is that? Because in the bathroom you're dealing with a small amount of light. In the burner you're dealing with fire. Fire has more light than the regular sunlight coming from the bathroom. So probably the one in the bathroom is very, very sensitive and has different limits. Everybody got that? So this is chapter 13 in the Smith book. They have some information about control that I want to go over. Let's go over one by one. Basic electronic components. We will talk about one function, electronic components, how to troubleshoot it. We'll see what the book says. So we don't have to go into the electronics and how they function that much, but we can understand that they are there. And again, this book describes all the electrical components, but there's also anti-short cycling timer. What do you think that is from the name? What is the time for the cycling? Remember when we covered, when the burner was running, we covered the eye, it cut off everything, right? So we don't want to restart right away. So we put a timer there that put and cause a delay. Sometimes 50 seconds, sometimes 45 seconds. That's anti-short cycling timer, so you don't go right away. And they also have that on air conditioners, sometimes up to 3 minutes. So if you turn it off on and off, it should take 30 seconds to come back. You have that also in case of power surge. There was a power surge, power outage. You don't want to shock the system, and you don't want it to come right away. So you put a timer there as a delay function. There's also a defrost module that will send, once you start accumulating frost in your condenser, your evaporator, you should shut off the system and start another component. What's a diode? For these, I just want to know the names, just in case you come across it, you know what it means.
It lets electricity only flow in one direction.
Excellent. Diode is a check valve. Why is it used? For many reasons. You don't want things to reverse, so you put a diode there, so the flow will go only from one place to another. That's a diode. Where do you always hear this word, diode?
We use them a lot in light bulbs.
Light bulbs, LED. LED is light emitting diode. So it has to go in one direction. So for LED, you cannot reverse the circuit. It's not going to work. Huh? It's small semiconductor component that lets the flow of electricity go in one direction. So for positive, negative, or not the other way around. Yeah.
Is it an arc? tiny little arc in a vacuum?
It could be. It could be for the light.
It is, yeah.
For the light. But for other components, it's different. But again, all I need you to remember is the diode is a check valve that the flow will just will go only one direction. The electronic module, that's basically a combination of transistors or small semiconductors put together to perform a function. So when you go into your car, probably you heard there's a computer module, there's a brake module, there's this and this module. A module is a combination of control that's supposed to do one function, and you have different modules for different functions. Electronic motor overloads, again, a bunch of sensors that will be put in the motors, so it will protect the motor from being burnt. In case it overheats, in case it overspeeds, but some of them are electronic. We encounter a few of those, but they're not electronic. We did deal with the thermal switch, where if the motor increases in temperature, it will trip. That's completely mechanical. We also have a centrifugal switch, big switch inside the motor that will click, that goes to control. However, some sophisticated motors, they have electronic control. Your transmission has some of that in your car. Probably if you're driving a car after 2000, they have electronic automatic transmission. It has a lot of sensors on it. It senses the temperature, it senses the RPM, it senses the oil circulation, and it will send you whatever. If something goes beyond the limit, it will signal you by turning on light. Light emitting diodes, LEDs. Why do you use those? Those are very, very helpful. This one has only one with many functions. It flashes back and forth. It can either steady solid or turn it off. That's the diode here. Small light is not too high in the amount of light it produces. It's just an indicator. New boards have a lot of diodes if they don't have an LCD. Now, because LCD dropped in price and it's very convenient, most controls, if you go to sophisticated equipment, they have a big screen on it with every diodes. It will tell you what it's supposed to be. Other ones, they will have a small light and a word next to it for indication. So those diodes are very useful. We can put them in a lot of circuits. And why did we use diodes in electronics than regular bulbs? Energy. They don't consume a lot of energy, and the circuit itself does not consume a lot of energy. The circuit is running in millivolts, and diodes work with very small millivolts. They can be dim, they can be high, and somehow in the early 2000s, somebody realized that we can use diodes with high energy to emit light more with the same efficiency. And this is how we start having LEDs. Rectifier. What's a rectifier? I'm trying to simplify it as much as possible.
Stabilize a current.
Huh?
Stabilize a current.
Well, what?
Stopping it from doing something.
Kind of. What do you think?
Doesn't it stabilize flow?
Kind of. So rectifier, from what I know so far, for our applications, it changes, it helps us change AC to DC. So what does it do? For example, if we have a wave, that is AC or DC? AC. So the rectifier will only shave the tops. It will only take the tops, which is either positive or negative, right? And DC is only positive or negative. So it will take those signals and put them in one line. And combine them together into one signal. So you can change AC to DC. Probably will go to a step down or step up. And probably you have that in your small phone charger. Remember the big charger in the past where they have a lot of coil in them to transform electricity from 120 to 12 volts for your computer. Now they're all electronic. So we have a small way to step down the energy from 120 to 24, and you have a small rectification system that will change that into DC. So see how small the USB charger is? This USB charger is getting 110 volts, but it's stepping it down into small size using a rectification system that is solid state to give you 12 volts or whatever volts you have, 4.5 volts.
So that can change to 5 volts.
It's kind of like a transformer, but in electronic way. Huh?
5 volts, 3 amps.
It depends from which USB you have. USB 1, 2, and 3. So that's rectifier. Solid state. We said that many times. What is the difference between solid states and not solid state? Solid state is something that's unmoving, no moving part.
So no moving part?
So the rise of semiconductors happened in the 60s and 70s when they realized that you can use a semiconductor that takes multiple semiconductor. So a semiconductor, in a simple way, acts like a relay. So let's look at this small, simple, rectangular piece of semiconductor. So we know when there's a conductor and there is non-conductor. Give me an example of a conductor. Copper. Metal. We have non-conductors. Anything that has carbon based, rubber, plastic, organic material, fibers. Semiconductors are in the middle of the periodic table. What are they? Glass, ceramics, silicon.
Where does water stand?
Huh?
Water
Water is a conductor. Especially if it has salts in it. Water is a conductor.
It's not a conductor, it's pure.
Huh? If it's pure, it's not a conductor. You know, it's only H2O completely, it's not a conductor, but things dissolve really easily in water, so it becomes a conductor.
So you're saying like if you use like purified water, you wouldn't get electrocuted?
Nope. Again, you might be the truth.
I'm not trying that.
Yeah. There's an experiment actually.
Yeah, that is true. As soon as you touched it, it wouldn't be pure water anymore. It would have the salt from your skin and it would get electrocuted.
Boom.
Depending on how much salt you have in your
Like
food.
drops out.
Not that much.
I mean, it's only going to your fingers.
Tim, I think you're the longest food thinking in your life.
10,000 volts.
Now I'm trying to understand how did you end up here. Okay, so semiconductor. What does it do? What does it do? So somebody realized that, okay, semiconductor, they conduct but when they want to.
These are like switches.
Give me a second. So remember a relay? In a relay, you activate 2 pins and it opens another gate, right? That's a regular relay. So here, for a semiconductor, this material is not conductive at all unless you put some current through it. It becomes conductor. You take out the current, it becomes non-conductor. It's kind of like water. Think about water with salt. You put in some salt, you're taking the salt out. So, and it has a connection in it.
So what materials are
Silicon,
That's like a big one.
yeah, that's why they call that place in California Silicon Valley. There's basically computers, and all computers have silicon in it. Let me show you a board. Can you have your board? So this board is full of semiconductors, LEDs, switches. Those are regular relays, mechanical relays. But this board is made out of silicon. And if you can see, there's no wires inside. They're small, printed lead connections. So this made things a little bit easier to make boards and make connections using semiconductor. Again, we're not going to go too much into electronics, but you understand the idea. A semiconductor is a material that conducts only when energized and become completely non-conductive. Well, not completely, but become highly unconductive when it's de-energized.
Is that what the green things are?
Yeah.
So it's like a switch, it turns something on, it turns something
Yeah.
off.
So you energize it, becomes conductor, it turns the switch on. So if you look here, you energize it, this becomes conductive. and if you de-energize it, it's not conductive. And based on that, we can accumulate a lot of logic. So the first computers that were based by, you remember, if you hear about the mainframe, the computer was as big as this room, and it was full of boards, and those boards were full of those little, small relays, mechanical relays. So every gate, every relay, it's basically making a decision, right? Either on or off, on and off. On is 1, off is 0. That's the whole basis of binary decision. When they say binary, it's 0 and 1. So 0 and 1, 0 is no circuit, no current, 1 is there's current. So a combination between 0 and 1. And that's what we have for semiconductor, bunch of relays. I mean, they're getting smaller and smaller to do those decision making. And the microprocessor, that's what it does. It has hundreds of millions of gates in it. So when they say the processor has 3 gigahertz, that's the amount of connections in it that make decisions for 0 and 1. It's a processing power. Transistors, small components, electronic components.
Skip thermistor.
What is a thermistor? I'm sure you took that in the refrigeration class. Let's write it down. Thermistor. A thermistor is a device that changes resistance based on temperature. So it looks like the cat cell, but the input is not light. It's temperature. You see it in fridges, you see it in ACs. That's a thermistor. Transistor, small component, again, semiconductor that can transmit signals. I don't think you need to know that. We're not going to go into it. Triac, it's very similar to a diode. Again, you don't have to know about that too. Varistors, we're not going to get into it. Too much electronics. Voltage spike, from what it means, sometimes the system, you have a malfunction and you have the voltage increasing really high, and you need something to protect you against that. Something will open up when you have too much voltage spike. So disregard the last 3, I don't think you will need them. So this is what I talked about. In the last 50 years, when we used to use logics and relays, this is an old relay, vacuum tube relay. They were mechanical, and it has a vacuum, so the vacuum will enable it to perform faster. There's no air inside, and it won't rust. And it gets smaller and smaller until we have a small semiconductor and diodes. So this took the place of this big vacuum tube. Does anybody have a vacuum tube amplifier? That's very expensive. What is it, Macintosh? So the vacuum tube, as when you used to have an amplifier, you used to have vacuum tubes in it, and these are the vacuum tubes. They're very expensive, they're very bulky, and they do apparently a great job in the music industry.
Still refer, we'd rather have them than solid state amps.
Yeah, that's true. Solid state, they do the job, but not the same. So digital is always faster, smaller size, but they don't give you the same size. Example, for somebody in the music business, why do DJs always like to use vinyl?
Get the best sound.
Huh?
Get the best sound.
Yeah, why? So when you play music live, of course there's nothing like live music. The sound will be different. I'm gonna divert a little bit just for entertainment.
They also scratch the record.
Huh?
They scratch up the records, that's probably why.
Yeah.
Now they got one
So-
for CDs.
When we talked about waves, we said every wave is a sinusoidal wave. So as I'm talking right now, I'm making waves with different modulations, high and low. I'm basically modulating my voice to make different waves. So if you do any kind of, anybody here like do mixing and stuff?
You ever see guitar strings that have slow motion?
Yeah.
That's kind of like what we're talking
So
about.
we have a wave. Let's say Lincoln is beatboxing, is that what they call it?
Engineer.
What he's doing is he's making a lot of waves, just like that. Big one and little ones. So for us to transform that from actual analog, this is the analog wave, to digital wave. What is digital again? Digital is binary. Binary is what?
Numbers.
0 and 1. So what we will do is we'll approximate that into small little squares. So you can see that there is an area here that I didn't account for. As small as I make those squares, as more I'll get accurate to the actual wave. But you will never get the exact same sound. So when you do analog, like cassette tape or vinyl, you'll get most of those analog waves. When you transfer that into digital, you're gonna have to have smaller and smaller and smaller rectangles over time to be able to represent that.
So
That way.
it wasn't a simple process going from the analog to digital.
No. So another, guys, another comparison, again, music. When you buy a CD, like you buy somebody's CD, how big is the CD? How many megabytes? 750? So the one song is around 35 megabytes. This is as close as you get to the vinyl or the actual recording. It's not going to be 100%, but it's very close to it because you have a lot of information. You have small little squares. When you transform that into MP3, how big is the song? 3.5 megabytes? 4 megabytes? So, yeah. So what happens here? You're losing a lot of details in the song. And if anybody, no matter how like in tune you are, if you hear a song on a CD and you hear the song in MP3, it's not going to be the same. You can tell the difference because there are so many details we just took out. We focus on his voice, the drums, an instrument, but there's a lot of waves in between, a lot of voice that we did not account for, and that's why it sounds different. So,
all the extra stuff, bells and whistles.
yeah, that's why you always prefer to have live music and you hear somebody sing live because you get all the details of it, and the more you compress, the more you lose information.
It's like
And I'm
pictures
talking-
too.
Huh?
It's like pictures.
Yeah, it's the pictures.
Like JPEG.
You are pixelating the pictures, you're getting more and more details, and that's why they have they used to have high definition, more pixels. Then they have the 4K, more pixels, so you have more definition. Again, you'll have more definition, but it's not going to be the same as the right picture because there's always going to be some details that you are missing. But the more you pixelate, the more you actually zooming in.
Prettier.
The more you take the same picture,
Yeah.
the less you're gonna see.
Exactly. Any questions? Watch the video. It's had a lot of. Okay. We done? So solid state, it's a physical description of the component. So when you look at that, is this solid state? No, this really. It's not solid state. This has mechanical components in it. It's moving. That is not solid state. Is this chip here solid state? Yes. There's nothing moving in it. So solid state, there is no moving part, guys. Semiconductors, it's based on the electrical conductivity of the material. Some geniuses thought of using semiconductors as our way to make logic and open and close gates. And they play a very important part, and that's how things got smaller, smaller, and smaller, and that's why you can have a cell phone that acts like better than the mainframe that was as big as this room. It's a small chip processor, and now they make microprocessor or nanoscale, thing that you can't even see. So it gets smaller and smaller. They use good conductors, copper, silver, aluminum. What material do they use for your processor? Platinum and gold. Because every microvolt matter. So let's think of the mainframe that used to be a computer as big as this room. and all those relays opening on and off, with even if one out, how much power do you need? A lot. So as you get smaller and efficient with less resistance, you'll kind of use less and less battery. So that's why again we can have small computers that you can carry around because they are using less and less electricity and doing the same function. So the smaller you get, the better in that regard.
How much postage would computer mainframe?
Computer?
Yeah, like mainframe is the screen.
I don't know, but it used to have its own generator. It used to really be huge. And you have amplifiers and you have conductor and transformer. And again, good conductors and poor conductors.
Did you ever see the imitation game? Where,
Huh?
where it all, the imitation game
Yeah.
where it started?
Yeah, that movie was really good, and it was all switches. All switches back and forth. And again, a room full of switches. Yeah. Back in the days, they used to use switches. They used to use people to switch phone calls.
Tape. Tape for a while. Put the
Yeah,
thing in.
actually, it was actual switch. There are people there in New York City or big hubs. You call and tell them, give me that number, and they will go. Actually, they connect you physically.
It's crazy.
There was a lot of job people in roller skates.
What was that, in the 70s?
Yeah. Where did I see that? It wasn't a movie. It was
in the 30s.
30s?
Like Abbott and Costello.
the beginning of, huh?
It's in Abbott and Costello.
I saw it in some movie where actually they employ people on roller skate to take the wire and connect you to this person. So that of course was overtaken by computers and semiconductors and logic. What do you mean by logic? Again, we said we have 0 and 1.
Yeah, phone booths. I remember phone booths. They still got those in England.
They were like a nickel, and they went up to like 50 cents, 75 cents.
So these are the very, very basic ways of making logic into a small controller. Or AND gates, both semiconductors, or they can be mechanical relays. So for the OR, this has to be on, off, only one of them. For this to be on. And this has to be on, on. If one is on and off, it's not going to turn on. Why is that important? Like in college, we had to design the logic of traffic light in an intersection. The logic for that using on and on gate was really huge. Like we had a board this big to make it with just OR and AND gates with actual switches. So if somebody's here, if this is on, this should be off. If this is on, it should be off, and on and off gates.
So our lights, are they caused by pressure plates or by timers?
Now they have timers. They have timers. They have
Those bulbs.
yeah. And some cities actually they have smart lights. Or actually there's a sensor. If nobody's in the street, they'll open it.
Sensor will interrupt the
Yeah,
timer.
yeah. So if it's all empty, why should you be stopping in the intersection? It will open that gate. Yeah.
Yeah, how would you get it? Like, why are those things?
Huh?
How would they get it?
These are means to control the flow. So if this has energy and this doesn't, this still going to be on, and it will make a path for this to go on. So don't worry too much about it. This also have power coming to it. If you're interested in this kind of stuff, you should go to electronics, and you'll get a lot of this. I'm just giving you a taste what it means. So our OR and AND gates are basically relays that control what comes out and what comes in. The idea is to tell you how we shrink things from having relays this big, something really small as this. And if you look here, each one of those relays has a capacitor, small capacitor, and small semiconductor. Diodes and rectifiers, simplest of solid state components. They're all different in size. Diode, again we say, what's a diode? A diode is like a check valve. It allows the current to flow only in one direction. So if you reverse the flow, it does not come back. Diode, component rated for less than 1 ampere. The flow only goes in one direction. So diodes are less than 1 ampere, so that's what we'll use in a board. Rectifiers have similar components, but it's bigger than 1 amperes. What do we use a rectifier for?
Change from AC to DC.
AC to DC. So probably, yeah.
You said it was similar components with the drive that changes AC to DC too.
It does that, but it has to be less than 1 amperes. What is the amperage for your charger, for your phone charger?
Amperage.
It should say on it. Sometimes it's milliamperes.
Probably.
Do you have a charger? So this is a regular iPhone charger, and it should say on it. So, but if you look at it, the amount of output is in milliamperes. It's very, very small. I can't see it. It's supposed to be very, very small. Okay?
Peak 0.15.
Milliamp?
1.6 amps.
It says 50/60 hertz, 0.15.
Okay. So the difference between diode and rectifier is the size, the amount of amps that goes through it. Yeah. Do you even look at those pictures?
Huh?
You look at them? The pictures.
Oh, no, you just take some down.
So,
Yeah, he does look right.
transistors, I'm not going to ask you about them, just to give you information if you're interested, but it's not going to be something you will encounter a lot. Composed of N-type and P-type material. It's a different material, and those are used for transmitting signals. If you go into electronics, probably you'll have to design boards that have N-type and P-type transistors, and that's based on the chemical in it, whether it's going to pass the positive or negative charge. So these things are important for when you have transmitters. How would you use transmitters? You transmit a signal from one component to, come on guys. You transmit a signal from one component to another. For example, we talked earlier last week about your tire pressure. What does it do? It has a battery in it, it sends the pressure and sends the signals to the computer. And it always breaks. So those signals make a difference. And how do you transmit them and how do you receive them? I'm not going to spend too much time into it. You need to remember that. Too much. Track, electronic control with 2 diodes in a single device. Used to switch as switches in AC circuits. So again, same as it has a track because of 3 paths. Same idea as semiconductor. There's a path here, but it's not going to be available unless you energize the 3rd path. So very, very similar way to the diode. But if you look at those again, let's look at those. This is a mechanical relay. It's heavy, and it has components in it, like moving components. This is the new one. Let's look at it. Nothing is moving. This is my new control. Nothing moving. Completely solid. And these little dots here basically are connections. And we have the LCD screen. It gives you the command. But if you look closely, look how small those printed controls are. So, can you pass this around? I will show you the old one too. Let's open this one.
Using gold in them?
No, probably like some polished copper with nickel.
That's where all the old computers are.
Yeah. So look at the old one. There's this is mechanical timer, mechanical relay. More possibility of being broken, and it does not do the same function that you get from the new one. and this is the old ones. So this is the advancement we have using semiconductors and electronics.
Memorize
No.
the sign.
No. LEDs, we know LEDs, light emitting diodes. Those are the lights we get in a lot of boards, and basically they tell you whether the circuit is on or off, and they can use it also to flash, be solid, and that can be interpreted in different ways. So for example, if you look here, diagnostic light is only one light and it's safe. If it's on, it means there's flame. If it's off, no flame. If it's flashing, it tells you something. I'll pass this as well. You can look at it. We're not going to go to a lot of controls for now. We're only going to use 4 major components for control. Primary control, aquastat, zone switching relay, and zone valves. We only covered one so far, which is what? No, the primary control.
Oh, yeah.
We did it cover zone valves.
I thought we were
Look at it. This is for you to change the time. Yeah. So it says valve on the board. It could be blinking for diagnostic, and they get a little bit involved too. I think I have some controls here.
So you saying that we never went over aquastat?
Huh?
So you said we never went over aquastat?
I'm pretty sure we
No,
had like.
no, we didn't went over, but we're not wired yet. Okay, check out this baby here. This control was electronic control from the 70s. Look how involved it is. This was in its heyday, probably was like around $2,000. $2,000. You can't get like $5,000 for it now. This is a primary control for industrial. It has so much logic and so much control. And here you see the module. So you can change the module completely. What is this command you of? Yes, Atari. Does anyone know Atari? You blew on it back in the war. Remember that? Say that again? Still around $5,000. Yeah, it's very, very sophisticated. Look at this. This was really intricate. You don't play with it. They don't even want you to open it. But this one it's all I'm going to look at it. And this is made in America.
Oh.
So they are still made in America, and probably different components. But why am I changing this? This will change the entire logic. This is the program here, the sequence of operation. We'll talk about that a lot again when we do it. Yeah, that's kind of the processor and the motherboard, and this is the program. You can change the timing, you can change the flame signals, whatever you want, and you put it in here. Look at it. What are these? LED lights. So each one of them means something. I'm gonna pass it on. Don't drop it. Oh, you can drop it. Yeah.
This one you can change the lockout time.
Yeah.
Yeah.
What it says.
I know, it changed the delay for the valve.
So
Yeah. There's a lot of things made in mass here, including railroad. Thermistors, we talked about them. It was here. Resistors that change resistance with temperature. Don't worry about the types, but it's a way to measure temperature. You'll see them in refrigerators. You'll see them in ACs. If you open up your window AC's front, and you'll see the evaporator, you'll see a little bit of a small little component stuck in it with a wire. That's a thermistor. When it gets too cold, like below 0, I mean 32 degrees Fahrenheit, they start to disengage the compressor and turn on the fan. Why? What happens at 32 degrees? It will freeze. You start accumulating some frost. If you have frost with the radiator, air is not going through it, which means the AC is not functioning. This is industrial belt, and when you look at power the AC voltage from 120 to 480. Whenever you have AC, current, you always can expect spikes. Spikes. So remember, if you were born in the 90s, no, if you were in the 80s and you had to buy a tower computer, and they tell you to buy a power stabilizer, you had to buy a power stabilizer, otherwise you void the warranty in the computer, because what happens is there's spikes in power for some reason, thunderstorm, something from the power company, and the voltage goes from 120 to 300 in a slight second. A computer is a very sensitive component, so it can ruin your computer and the CPU will be damaged and you'll have to change it. So power spikes are always anticipated whenever you have AC, because AC is a wave, any spike in the wave will go all the way into the circuit. It's kind of when you have that rope game, if you swing a rope, one spike will go all the way to the thing. It will diminish, but it will still get some of it. Come on, they have to grow. It's gonna get longer. It's gonna get longer as long as you talk. So now we have all the controls in one board, and you can see how small, lightweight, and concise it is.
Little people make them things?
Huh?
Little people make them boards?
No, actually, those get printed by machines now. They are not done by machines. Mestic in Westfield, they print boards like that. You can buy a machine that will print you all these components. You put in the computer what you want, and you have a blank board, and it will go there and spot solder all that. I don't think a human being can do all this precision in printing and spot welding. It's possible to do one or two maybe, but imagine doing all this. It's gonna be like a week job. Yeah. Some people actually make money doing these boards.
I got a rework station, at a certain point you can't do it. With
Yeah.
all the IOAs and stuff on there, that's too small.
There are some hobbyists who will rebuild your car computer for like a fraction of the price of your computer. If your computer in your car burns, any car, it's gonna be up to $2,000. When the computer is gone, you jump the car for any reason. If it's not under warranty. But you can have some hobbyists in their garage that will print you the module just like this. They have a schematic for every car, and they will do the board for you for like $300. Or fix whatever wrong with the old board. They'll go trace the circuit, and they find one of the transistors gone, they will change it for you. Again, the manufacturer will not fix things, they will just give you a new one, which is very expensive. I had a car where the computer was gone, the computer was $3,000. I got it fixed for $500. Something in the brake modules went bad, and they fixed it. And if you want to buy a computer from the junkyard, it's not going to work.
Gotta have flash.
Yeah, because it has the VIN number of the car. So it has to be hooked up with that VIN number of the car.
Wait, is that procedure?
Yeah, car computer will not be swapped easily. You have to reformat it.
They do all that shit on purpose, man.
Well,
It's all a scam.
Again, if the car is in the warranty, it should be covered. Otherwise, they want to make money out of it. And there's ways around it.
3G.
Simple electronic temperature controls. This is about thermistors. We'll have a thermistor is an input circuit. It varies with resistance as the temperature changes. Amplifiers. What are amplifiers? What do they do? They exaggerate whatever signal they get, from small to higher. And luckily, they will keep. If you have an amplifier in your car, what does it do? All the signals coming from the radio will be amplified and sent out with bigger waves. So the same thing here. Some of these components here, they send micro volts and microamps, and sometimes you have to amplify that signal by a factor of 10, 100, or 1,000 for you to have action with that. Example. a sensor sends a signal that the temperature or the gas flow is low. That signal sent to another amplifier that will send the signal with 120 volts to a valve to open. So you always need an amplifier to increase the signal, or an amplifier also to change the signal from high to low for you to read it in a small board. If the board usually runs with very microvolts, very small amps, and again, you cannot run this with line voltage. This will burn. And that's why it has, the first thing it has is transformer. So at most volts are around 124 volts AC. We talked about that. Timers. Timers are very, very interesting because this is where we do. Let me see if I can spot one here. If you look at this little box over here, that's less than 2 millimeters, that's a timer. You can go to, if you're a hobbyist again and you build your own boards, you can go to Radio Shack and buy a timer of 10 cents or something, it's small AC. So you can connect that to any light bulb or something, and you turn on the switch and it will take 2 minutes to turn on. So timers do great service. They're very compact and easy to install. You can have a picture of it. Delay on make timers, don't worry about that. Another form of timer is the anti-short. To avoid spikes, you don't want to turn things on and off right away, especially if there's a motor, because that will cause a shock, and you can also cause if you have a short in the circuit. From 30 to 5 minutes. There are some delay timers here, and there are probably at least 4 or 5 in the industrial control one. This is going to go on for a long time. Are you paying attention? So skim through it.
What's the last one? 5 seconds to 5 minutes?
5 minutes.
30.
Yeah, 2 cycles. Again, if you go into controls, and if you get a job where you have to go on program controls, you understand all these things. We have 3 or 4 students from this program who went to Siemens Control, and their job is just to identify those components and know what always goes wrong. So when they go and they find something is, for example, there's supposed to be a delay of 3 minutes, but suddenly there's no delay. So they know which component to take out and replace. Most of those components that are prone to be broken, they are plug and play, where you can just like put them into the board or take them out of the board. Anti-shorts. So for us, for our intended purposes, this control is a black box. We do not change anything in it, but we have to know for sure that this is broken before we change it. How did I know that this thing is broken? Who was working it? Who was working with it? In the lab.
I was using
Was us?
could be both.
Was it you? I don't know. It wasn't one of the boards, and we tried to, I think it was Sean Garvey. Yeah. So we were working on it. It had no power. It was dead. So we diagnosed the circuit. We made sure it's receiving power. Guys, we made sure it was receiving power. It's still dead. Then I opened it up, and I looked inside, and if you look at those 2 pins, you can see how burnt it is. It is burnt. So that means that the board is gone. I can't fix it. I will just change the entire thing. You're not supposed to fix it. It's 80 bucks. That's not that bad. That's reasonable. And just change it. So we treat the whole thing as a black box. You do not open it. And a lot of warranty is provided once you open it. And you care about the input and output. You can read the instruction manual and see if there's some kind of signals that you can interpret and fix. There's a lot of fault messaging system. Even this one has a fault system, as you can see. If it flashes, it means something. And again, if it's dead, something wrong completely with the control. And sometimes one of the is still on, but something is wrong with it. With these ones, where did it go? With these ones, you can still have power, it can still function, but not properly. So this was really annoying and takes a lot of time to diagnose because you don't know what's wrong with it. and you want to take your time knowing if it's wrong or not. According to Bill, those are still being sold and they're still being used, and you can replace it with the same. But it is easier always to replace with the same component because you're not going to change anything in the wiring. However, if you want to do the customer a favor, you can upgrade to get another one. So that concludes my. We're not done yet. I have 15 minutes. Chill. This is chapter 13. Huh? Yeah. This is a book. Has a lot of information.
I just bought it.
Yeah.
Yeah, I was able to get the last one of these.
Yeah. If you look at the chapter 13, you see a lot of electronics. Skim through it, and it has good information. But that's the last chapter I want to talk about in Smith book. After that, you'll see a lot of heating controls, a lot of controls for ACs and
To read through and do the questions at the end?
huh?
To read through and do the questions?
No. So there are some reference books recommended, but you don't have to have them. That's that safeguard control by Honeywell.
No funny shit, actually.
The documents that you will need, the documents that I will need you to have, I'll put in the blackboard. So you don't have to buy that book. What's going on?
No lotion.
No comment. No comment. No comment. Nora. This is the book that we're gonna start using from now on. We'll spend 10 weeks talking about this book. I hope you have it. It's in Blackboard as PDF. And we'll start reading this book one chapter at a time. Hopefully we'll be done by week 12. Then I'll do some industrial stuff. If you master this book, you can take the NORA oil burner exam, which also gives you a good certification. And you can also take the Massachusetts oil burner exam. The NORA organization is based in New Hampshire, and if you work in New Hampshire, probably you need the NORA certification. If you work in Massachusetts, you need the Massachusetts oil burning certification.
Will that help you with the Massachusetts one?
Yeah.
Oh.
Actually, recommend that book here.
Is there a different oil burner exam for every state?
Yeah.
Right.
But if you take one, some of them will transition. I believe, I'm not sure, but the Massachusetts license is valid in Connecticut, but you have to take, apply for it.
So what would be like the differences between like these three?
Code. Different codes.
I mean, I get it for mine.
Huh?
How many retakes are
Infinity.
No kidding?
Yeah, every time you're gonna pay.
Oh, $75 every time?
Yeah.
And you gotta drive out an hour, right?
Yeah. So I'm trying to get the, not final yet, but I'm trying to have the, as part of public safety come here and give us the exam. We'll see how that works. We'll try. Okay.
Is there a book for
I have 10 minutes. Do you want to leave?
Yes, sir.
12:30 is 1:30. No. Some of you have class.
Yeah.
Okay, that's good for now.